In 1972, the meteorologist Edward Lorenz suggested that a butterfly flapping its wings over one continent may cause a hurricane in another. This concept was termed the butterfly effect and stands as an example of how seemingly insignificant approximations can transform into huge errors over time. This video will explore different applications of the butterfly effect in fluid dynamics. Like many meteorologists in the 50s and 60s, Lorenz was determined to develop a method of predicting weather far into the future. He created a computer program that stripped the concept of weather down to its bare skeleton, temperature, and wind. Each minute, the computer would mark down a set of numbers to represent wind speed and direction. In 1961, Lorenz decided to take a shortcut in re-examining one of the sequences. He started the simulation midway through instead of from the beginning, typing in the initial conditions straight from an earlier printout. Within the hour, the original and new wind patterns differed so widely that there was no evidence they had started out with the same conditions at all. The issue? Lorenz had made a critical mistake. The numbers he had entered back into the program from the printout were rounded versions of those stored in the computer's memory. These bits of information, so small that they were in the 4th, 5th, and 6th decimal places, had created such a wide difference in the trajectory of this wind. The butterfly effect extends far beyond just meteorology. For example, take a look at the convection currents in this bowl of water. As the water at the bottom heats up, it loses density, rising above the cool water and pushing it to the bottom, where the cycle begins again. Simple, right? Wrong. That model of convection, which is usually taught in high school science, ignores a laundry list of small occurrences that render the exact patterns of convection currents unpredictable. Lorenz expressed these complications through an analogy of a water wheel, a wheel holding cups with porous bottoms, and a steady stream of water pouring into the cup on top. Just as hot water will rise over cool water with lower density, gravity will cause the wheel to turn, so the fuller cups are at the bottom. When the heat in the convection system is increased, the water begins to speed up, just as more cups filling with water cause the water wheel to move faster. Eventually, a cup will reach the top of the wheel without being sufficiently emptied, and the wheel will slow down, stop, and change direction. Similarly, the water will not be sufficiently cool when it reaches the top of the bowl, changing the flow of the convection currents. Coincidentally, the actual equation describing the Lorentzian water wheel produces an image that resembles a pair of butterfly wings. And although there is an overarching path, the trajectory of the wheel never intersects itself. The same result will never occur twice.